You're listening to Skeptoid. I'm Brian Dunning from Skeptoid.com. On Washboarded Roads. Today we have a really neat general science puzzle for you. The problem is that of washboarded dirt roads. Unpaved roads that, over time, develop a rough, rippled surface that make them incredibly uncomfortable to drive over, to say nothing of the extra beating they give to a vehicle's suspension. We would love to solve this, as dirt roads are the only practically inexpensive way to reach countless remote destinations worldwide, and the washboarding that inevitably develops can make such trips intolerable. In order to solve this, we have to first understand why and how it happens, and that's why this little conundrum became a Skeptoid episode. The problem is so bad in places that local governments have been willing to spend money to research it, resulting in decades of published papers filled with physics equations. Exactly what do we know so far? Put on your seatbelt, sit on an extra cushion, and let's go find out. As a longtime desert rat, I've hammered out a lot of miles on dirt roads in the Mojave Desert and the greater Colorado Plateau. The Skeptoid monster Jeep has been just about everywhere there is to go. To mitigate the discomfort of rough roads, most off-roaders, myself included, deflate the tires down to a very low pressure. I use 10 psi, which makes the rockiest trails feel like a comfort cruise. But even this provides only so much help with washboarding. Seasoned drivers know that there is a sweet spot you can find, whereby going at exactly the right speed, your vehicle will glide right over the top of the ripples and you won't feel hardly a thing. Now, I have no idea what the science behind this is, whether it depends on the size of the washboarding or the vehicle's wheelbase, or whether it's to do with resonance or what. But in the Skeptoid monster Jeep, this speed is 52 miles per hour, 84 kph. Now, quite obviously, that is an unsafe speed on a dirt road, but I've probably done thousands of miles like that. The dangers are many and very real. You have no meaningful traction flying over the ripples like that. You can't brake or steer effectively. Desert roads are usually sunken a bit below the surface and they're lined with tall shrubs, so visibility is extremely poor. You can't see another vehicle coming in time. One time another Jeep traveling with me suffered a rollover, totaling the vehicle but causing no serious injuries, which was only blind dumb luck. This is very dangerous and you should not do it. I only do it when the road is straight as an arrow and I can see far ahead, and I'm familiar enough with the road to know that there are no surprise dips or washes cutting across, both of which are common. Even still, it is very, very high risk. I'm pushing the envelope every time, and I drive with a level of extreme vigilance beyond any other state of consciousness I possess. Do as I say, not as I do. The reason I mention this is to underscore the degree to which washboarding is a real problem for travel and commerce, especially in places like Australia and Africa where pavement is impractical. The alternatives to my method are to drive at a normal speed, which destroys the vehicle and still makes the surface unsafe, or to drive at a ridiculously slow speed that's just not workable for long distances. Research has shown that 5 miles per hour, or 8 kph, is the fastest you can travel without contributing to washboarding. One of the first things we can deal with is the popularly cited belief that ripples on a road are the same thing as ripples on the bed of a river, or anywhere water flows over sand or sediment. This is sort of true and sort of not. Both processes are started in the same way, by exactly the same forces, but that's where the similarities end. With water flowing over sand, stronger influences take over from there, turbulence and vortices, which are not part of the equation when a car is driving down a dirt road. That turbulence, with all of its complex fluid dynamics, is the primary driver shaping the waterbed ripples from then on. The same goes for wind ripples in sand. Wind ripples start small, and over time, as the wind continues to blow over them, they merge and grow, eventually becoming large sand dunes. We make the same observation with washboarding. Those ripples also start small, and over time, with the passage of more vehicles, they too merge and grow. A washboarded road with the highest ripples spaced the farthest apart, is the oldest. This is one of the first and most surprising observations that scientists have made about washboarding in the era of modern research into the subject. Our intuition suggests to us that vehicle speed or tire size or the type of surface is what determines the scale of the rippling. Nope, regardless of all other factors, washboard ripples start small and gradually grow as more vehicles pass over. Another surprise is that we can now conclusively dismiss what was for a long time the standard explanation for washboarding, and that's that a vehicle's sprung suspension is what causes the effect. For a long time, this was the only explanation you were likely to find. The tires would bounce on the springs, and those bounces were what made the alternating ripple pattern. Or the lightweight bed of a pickup truck would bounce along and cause it. Often this explanation would incorporate the sand thrown by the drive wheels at each point where it makes contact, building up the next ripple like skiers pushing snow into moguls. However, it turns out that all of these, everything pertaining to the springs or the drive or the bounce of a vehicle, have nothing whatsoever to do with washboarding. And here is how we know that. What researchers have typically done, in addition to computer modeling, is to set up a large rotating surface covered with sediment and then lowered a wheel onto it, in such a way that the wheel traverses the same path around the table over and over again. This allows them to experiment with all kinds of wheels and all kinds of surfaces. It seems almost barbarically simplistic, too much so to be useful, but more than one research team has done this in concert with computer simulations, and it turns out to match the data and the predictions. Here are some of the interesting things learned. Number 1, the type of sediment makes no difference. Washboarding will appear whether it's sand, coarse gravel, or a mixture intended to be as stable as possible. The more stable it is, the slower the ripples will grow, but they still grow all the same. Number 2, whether the surface is wet or dry makes no difference, but the ripples grow fastest when the sediment is driest. When it's wet, the water acts as a binding agent and makes it a bit more stable. Number 3, the size of the wheel makes no difference. Heavier wheels will make the ripples grow faster, but they still grow in the same way no matter what characteristics the wheels or the suspension have. Number 4, traveling faster makes the ripples grow faster. The slower you go, the longer it takes ripples to appear and grow, but when they do, the size and characteristics will be the same. Below 5 miles per hour, or 8 kph, no ripples were observed to appear. Number 5, as the ripples grow, smaller ripples merge, and all the ripples move around a bit throughout this process. Some move forward with the direction of vehicle traffic, and some move backward against it. Previously, it was thought that they always moved with the direction of travel, but that's not so. Number 6, it doesn't matter if the wheel is driven or not. Previously, it was believed that wheels exerting lateral force against the surface, whether braking or accelerating, were the cause of washboarding, but freely turning wheels cause it just as well. However, the more lateral force exerted by the wheel, like if it's strongly accelerating or strongly braking, the faster ripples will grow. This explains why washboarding is more severe at places on the road where vehicles brake or accelerate. Number 7, washboarding also happens when the wheel is locked and skids over the surface. It doesn't even have to be a wheel. Even a flat metal plate dragged along the surface will cause the same ripples. Rolling wheels tend to make the ripples move forward over time as they grow. Solid dragged objects tend to make the ripples move backward over time. Now here's one that might blow your mind. Railroad tracks also get washboarded. Do an image search and you'll see that old, heavily used railroad tracks will eventually develop a scalloped surface, and that's washboarding. A steel railroad track is obviously a lot more stable than a dirt road, but a train rolling over it is also a pretty severe use case. Washboarding, it turns out, happens when any malleable surface has a lateral force across it. Even in the steel of a railroad track, each passing train pushes some of those molecules forward every time. Now, researchers have formulated equations describing all of this, but they're probably not worth going into here, as they don't offer a simple, this many cars going this fast over this kind of surface will make the road this washboarded in this amount of time. No, it's all way more abstract than that. The best you're going to get is the Froude number, the ratio of the flow inertia to the external field. Now, if that's your jam, see the references for this episode at Skeptoid.com, and you'll have all the physics equations you'll ever want. What about concrete and asphalt roads? If it can happen to steel railroad tracks, why doesn't it happen on paved roads? So it does, but much more slowly. Let's start with concrete. Concrete roads are thoroughly engineered to be as hard and long-lived as possible. They are actually harder than railroad steel, averaging 6 to 7 on the Mohs hardness scale, while railroad steel comes in at 5 to 6. But more important than their hardness is their stability. The particles making up concrete are embedded in a limestone crystal matrix, which is substantially more stable than steel. Washboarding is forming, but way more slowly than anyone will ever see. Asphalt is a very different story. The key to asphalt's utility as a road surface is its resilience. It's like gooey rubber. While the forces from traffic are constantly trying to get washboarding started on asphalt, its elasticity is constantly pulling itself back together, which happens faster and more efficiently than the washboarding. This back and forth is one factor that eventually disintegrates the asphalt, necessitating replacement. So, can anything be done in remote places where long dirt roads are important and funds for paving are not available? Well, there are only 2 recommendations. The first is to use a specialized mix of specific sizes of gravel and fines that will be as stable as possible, slowing the formation of washboarding. But this would be nearly as expensive as paving and is not a practical solution for the kinds of locations we're talking about. The second is all they can do. Get a grader out there and scrape away the ripples to a depth of 1 inch below the shallowest parts, then redistribute that material over the surface. And basically, repeat this as often as necessary. And thus the question of how washboarding is formed is as adequately answered as we're ever likely to get. It is a surprisingly tough problem out in the real world, toughest where the solutions are needed most, and determining all the physics behind it has so far failed to suggest a magical solution. But it did help us to dismiss the earlier misconceptions. Deflate those tires as much as you can, and sit back, because it's going to be a long and bumpy ride. A great big Skeptoid shout-out to premium supporters Joe Benny, Mad Brad, Virginia's only skeptic, Ricky Baroud, and Randy Edwards. Sustainability is a popular theme in science, and the support from these premium members is what pays the bills of our nonprofit and makes Skeptoid sustainable. Please join them by becoming a member for just $5 a month or more at Skeptoid.com and click Go Premium. And while you're at it, get the Skeptoid books. They make great bathroom reading, and they're awesome gifts for people who don't listen to podcasts. Get them in our online store, along with all your other Skeptoid swag, at Skeptoid.com/store. You're listening to Skeptoid, a listener-supported program. I'm Brian Dunning from Skeptoid.com.